Imagine two coins separated by miles, yet always landing on the same side instantly. This is not magic or trickery. It is a glimpse into one of the most profound phenomena in the universe. Quantum entanglement connects particles in a way that defies classical logic. The moment you measure one particle, the other responds instantly, regardless of the distance between them. This is the universe speaking in its own secret language. Prepare to be amazed as we unravel this mind-bending reality. Entanglement means that two particles are linked so that their fates are intertwined. It does not matter if they are a meter apart or light years apart, the connection remains. When we examine one particle, its state is instantly mirrored in the other. This idea seemed so impossible that even Einstein called it spooky action at a distance. He could not accept that physics allowed such instantaneous connections. Yet over decades, experiments have proven him wrong. Entanglement is not a flaw in the theory. It is a fundamental property of the quantum world. To understand how entanglement works, imagine two particles created together in a laboratory. Their properties are defined only relative to each other. When we measure one particle, we find its state instantly determines the state of its partner. This is not faster than light communication. It is a correlation that existed from the beginning. The particles share a pre-established harmony that classical physics cannot explain. This defies intuition, yet the experiments consistently confirm the phenomenon. John Bell provided the key to testing these ideas. His theorem allowed scientists to distinguish classical explanations from true quantum entanglement. In the 1970s and 1980s, experiments by Alan Aspect and later Anton Zeilinger confirmed that entangled particles behave exactly as quantum mechanics predicts. No local hidden variable could explain the correlations. The results shocked the scientific community. Reality itself was forced to reveal a deeper level of interconnection that had been invisible until that moment. Entanglement is not just theoretical curiosity, it is powering the next technological revolution. Quantum computers use entanglement to perform calculations that classical computers cannot. Qubits in entangled states allow simultaneous processing of enormous possibilities. This means problems once thought unsolvable can now be approached in practical timeframes. From simulating complex molecules to optimizing supply chains, quantum computing is transforming every aspect of science and industry. Another application is quantum cryptography. Secure communication channels based on entanglement are fundamentally unhackable. If a third party tries to intercept entangled particles, the system immediately detects the intrusion. This opens the door to encryption that cannot be broken, even by future supercomputers. Governments, banks, and private corporations are racing to implement these technologies. Entanglement is moving from the lab into the real world with astonishing speed. Despite the progress, there remain mysteries. One of the deepest puzzles is the measurement problem. When does a quantum state collapse into a definite reality? Does observation create reality or merely reveal it? Entanglement sits at the heart of this mystery. By studying it, we are learning that the universe may be far stranger than our senses allow us to perceive. Each experiment hints at connections that extend beyond space and time as we know them. Some theorists suggest entanglement could be fundamental to spacetime itself. The structure of space and time might emerge from the web of quantum correlations. If true, this would imply that the universe is not made of separate objects in a void, but a continuous fabric held together by entanglement. The implications are staggering. It could explain why gravity behaves as it does and offer clues toward a unified theory that reconciles quantum mechanics with general relativity. There is also a link to the holographic principle. Some scientists propose our three-dimensional reality is a projection of deeper two-dimensional information. Entanglement could be the thread that weaves together this projection. In other words, the seemingly separate events we observe are all manifestations of an underlying interconnected reality. Each particle, each photon is part of a cosmic conversation that stretches across the universe. The philosophical implications are equally profound. If particles can be instantaneously connected over vast distances, what does that say about consciousness and reality? Are we observers creating aspects of the universe by the act of observation? Does the universe itself possess a hidden network of connections that underlie everything we see? These are not mere thought experiments. They are questions that challenge the way we think about our place in the cosmos. Entanglement invites us to imagine a new vision of the universe, one where distance is an illusion and every particle is part of a vast interconnected dance. It encourages us to consider that the universe has a secret language, a way of communicating its underlying order that we are only beginning to understand. From the smallest particle to the largest structure in the cosmos, everything is entangled in a symphony of connection and correlation. As technology advances, we are starting to harness entanglement for real-world use. Quantum networks are being developed that could one day link computers securely across continents using entangled particles. Researchers are exploring how entanglement might be used to enhance sensors and measurement devices. Every new discovery opens the door to possibilities that were science fiction only a few decades ago. The universe is teaching us that connectivity is fundamental, not optional. The study of entanglement also reshapes our intuition. Classical physics tells us that objects exist independently and information cannot travel faster than light. Quantum entanglement defies both assumptions. Particles can act as if they are coordinated instantaneously, and their states are dependent on relationships rather than absolute positions. It is a new paradigm that challenges us to rethink what it means to exist and interact in a universe that is far more interconnected than we imagined. As we look ahead, the frontiers of entanglement research expand into ever more exciting territories. Quantum simulations might reveal new materials and medicines. Quantum communication could transform global networks. Philosophical and scientific inquiry into the nature of reality could reshape our understanding of time, space, and consciousness. The universe's secret language is becoming a tool for both practical innovation and profound insight. Next part can continue to explore the deeper implications of entanglement, philosophical questions, and emerging technologies. It will include examples of quantum teleportation, quantum networks, and the potential for entanglement-based understanding of consciousness and space-time. The narrative will remain engaging and broken into digestible paragraphs to maintain listener attention throughout a long video. Entanglement also challenges our notion of locality. Classical physics assumes that objects are only influenced by their immediate surroundings. Quantum entanglement shows that particles can influence each other instantly across vast distances. This is not a signal or a message being sent faster than light. It is a fundamental connection that exists independently of space. Understanding this changes the way we think about cause and effect and forces us to reconsider the very fabric of reality. Quantum teleportation is one of the most fascinating applications of entanglement. It does not transport matter itself. Instead, it transfers the state of one particle to another distant particle using entangled pairs. Scientists have successfully teleported information between particles across kilometers of fiber optic cable. This paves the way for quantum communication networks that are faster, more secure, and more reliable than anything classical technology can offer. Each experiment demonstrates the power and reality of entanglement in ways that were unimaginable just decades ago. In laboratories around the world, entangled particles are being used to improve precision measurements. Quantum sensors based on entanglement can detect gravitational waves, magnetic fields, and even minute changes in time with unprecedented accuracy. This opens new frontiers in astronomy, geology, and medicine. The ability to observe the universe with such precision relies on understanding and harnessing the subtle correlations of entangled particles. It shows that entanglement is not just theoretical, it is practical and transformative. The implications of entanglement for understanding consciousness are deeply intriguing. If reality is fundamentally interconnected at the quantum level, then observation itself may play a key role in shaping outcomes. Some theorists speculate that consciousness interacts with entangled systems in ways we are only beginning to comprehend. While these ideas